Hello everyone, my name is Ramya. I'm a postdoctoral student under Professor Grace Kaur in Aeronautics and Astronautics at Stanford. The topic of my today's presentation is on set-valued shadow matching using zonotopes. As we are all well aware, GNSS-based localization is often unreliable in dense urban areas. As shown in this left figure, line-of-sight signals can be blocked or reflected by buildings, creating non-line of sight and multipath. Consequently, high positioning uncertainty is observed using GNSS-only localization, especially in the cross-street direction. Now, while urban area is challenging, it also opens new opportunities. For instance, we can leverage 3D map of urban environment to aid GNSS by distinguishing line of sight and non-line of sight signals. There exist many high-fidelity 3D maps of popular cities across the world. The example 3D maps shown in this slide are that of London and San Francisco. The state-of-the-art on 3D map-aided GNSS localization can be divided into two categories. One is ray tracing and the other is shadow matching. Given discrete position candidates and 3D building database, the objective of ray tracing is to find all possible paths from the receiver to the GNSS satellite, while considering a limit on the number of interactions per each transmitted ray. Essentially, this method estimates the reflection route of NLOS signals and uses this to correct the bias in pseudoranges. The next one is shadow matching that utilizes CN0 to determine whether the receiver is inside or outside the GNSS shadow of each building. Here, GNSS shadow denotes the region where the line of sight signals are blocked. For predefined position candidates, this method predicts satellite visibility at each candidate using 3D map database and later evaluates the similarity between predicted and expected visibility to select the most likely position candidate. A common aspect of both these methods is that they represent position estimates in a discretized way. That is, one can use a finer discretization to achieve a more accurate estimate, but it comes at the expense of added computational cost. Furthermore, these point-valued methods also face challenges in ensuring that a position estimate obeys user-defined safety bounds. To avoid this point-value discretization trade-off, one can instead consider a set-valued approach to compute a continuum of state estimates given the initial set of states and measurement bounds. An illustration of this set-valued approach can be seen in this figure. Furthermore, the set-valued approach can be used to provide guarantees by checking if the final estimated position set lies within the user-specified safety bounds. In literature, many set representations exist for parametrizing the states. Among them, one strategy for modeling arbitrary set-valued state estimates is to use zonotopes. Zonotopes are essentially convex symmetrical polytopes that can propagate set-valued state estimates using fast vector concatenation operations. Zonotopes are widely popular in robotics for formally verified path planning and collision avoidance. Mathematically, zonotopes can be characterized using two parameters. One is center and the other is generator. An illustration of this set representation is shown in this figure, where the generators are essentially line segments that construct the zonotope. These can also be extended to constraint zonotope that represents arbitrary convex polytopes, thereby avoiding the limitation of symmetry. These constraints are mathematically formulated using A and B as shown in this figure. By applying these constraints to the blue zonotope on the left, we can formulate the green set on the right, which is essentially a constraint zonotope. We propose a set-valued approach in this work known as zonotope shadow matching, in short known as ZSM. In this, we design GNSS shadow using zonotopes where, if you recall from earlier, GNSS shadow is the region where line of sight signal is blocked. A visualization of this ZSM concept is shown here. To formulate GNSS shadow, we construct 3D buildings as constraint zonotopes. Next, we extend the building along the shadow direction of GNSS satellite to perform set intersection with the ground plane. Using GNSS shadows associated with each satellite building pair, we iteratively refine the initial set valued position estimate. Particularly, we use CN0 for identifying if the receiver is inside or outside the GNSS shadow. And if it's inside, we do set intersection, whereas if it's outside, we perform set subtraction. The key contributions of this work are listed here. Firstly, we design set-valued shadow matching with GNSS shadows as zonotopes. Second, we develop an iterative approach to refine set-valued position estimate by performing set intersection or difference with GNSS shadow, which is judged based on the CN0 values. Third, we validate ZSM performance using simulated experiments based on downtown San Francisco 3D map. To our knowledge, this is the first work utilizing set representations for 3D map-aided GNSS. The outline of the presentation is seen in this slide. I'll first explain our proposed algorithm on Zonotope shadow matching, in short known as ZSM. Next, I'll demonstrate the performance of our ZSM using simulated experimental data. In the end, I will summarize my talk. First, let's start with the details of the proposed ZSM algorithm. In the first step, which is executed offline, we pre-process the standard 3D maps that are expressed as union of triangles. We convert each triangle to a constraint zonotope. An example illustration of multiple constraint zonotopes associated with the triangles of a 3D building are shown in this figure. Then we utilize the convex hull property to combine the elements belonging to any of these constraint zonotopes to a single constraint zonotope, which is shown on the right. In the next step, which is executed at runtime, we compute GNSS shadow zonotope for each satellite building pair. An example illustration of this set operation is shown in these bottom figures. First, we design a shadow direction zonotope by considering the center to be at the origin and generator to be a scale unit vector from GNSS satellite to building center. Next, we compute the 3D shadow volume by extending the building zonotope in the shadow direction. More specifically, we use the property of Minkowski sum that adds each element in building zonotope with each element in shadow direction zonotope to compute 3D shadow volume as a constraint zonotope, which is highlighted in cyan in this figure. Next, we compute 2D GNSS shadow by projecting this shadow volume onto ground plane. This 2D GNSS shadow is represented by magenta in this figure. We execute set intersection to perform this operation, an example illustration of which is seen in these bottom figures. Essentially, set intersection identifies the common elements present in blue constraint zonotope and green constraint zonotope to compute the orange constraint zonotope. After computing GNSS shadow for each satellite building pair, we start with an initial 2D set valued position estimate. For any GNSS satellite, if the CN0 value is less than threshold, we perform set intersection of GNSS shadow with current set valued position estimate, and otherwise, when this condition fails, we perform set differencing. To illustrate this procedure, let's consider an example with 2 urban buildings and 7 GNSS satellites. Here, the blue circle marker indicates line of sight and yellow circle marker indicates non-line of sight. Let's look at the top figure for this illustration example. To start off, we consider an initial set valued position estimate that is indicated by the magenta highlighted region, and ground truth position is denoted by black circle marker. Since PRN-29 satellite in this case is line of sight, we perform set subtraction to remove the cyan region representing the GNSS shadow from the initial set estimate to obtain the current set valued position estimate, which is highlighted in magenta. Next, given that PRN25 is non-line of sight, we perform set intersection to identify the common region between the set valued position estimate and 2D GNSS shadow. The resulting set valued position estimate is highlighted in magenta. This process continues further where we sequentially go across all satellites. Particularly, we perform set intersection for PRN13, set intersection for 5, then set intersection for 26, then set intersection for 20, and lastly set subtraction for 21. Note that estimated final set valued position has high certainty along cross-street direction. Even though along street direction is not as good as the cross street, note that along street accuracy can be easily improved via aiding from other sources such as IMU pseudoranges. Now I'll talk about our simulated experimental results that validate the performance of the proposed Zonotope shadow matching algorithm. Particularly, we choose a simulated platform so that we can perform exhaustive analysis of our ZSM performance. For our GNSS setup, which is shown in this block diagram, we utilize off-the-shelf GPS SDR-SIM and soft GNSS to generate measurements for 14 visible satellites. We added simulated non-line of sight effects to the CN0 values based on 3D map and receiver ground truth position. We also utilize MATLAB Cora toolbox for set representations such as Zonotope, constraint Zonotope, and to perform set operations. As next step in our simulated experimental setup, we utilize publicly available 3D map of downtown San Francisco. The left image is the raw vertex representation in which we isolate the vertices pertaining to each building using the theory of connected graphs. Then we converted the entire 3D map from vertex to constraint Zonotope representation, which can be visualized in this right figure. In this figure, we observe that the notable landmarks such as Transamerica Pyramid and Salesforce Tower can now be easily identified. We validate our proposed algorithm by comparing against conventional shadow matching that is designed using a grid of uniformly distributed position candidates. Specifically, we consider 4 validation metrics: offline and online computation load, position error, and position bounds. For conventional shadow matching, we consider predicted satellite visibility in an offline manner, and at runtime, we compute visibility score by comparing predicted versus expected visibilities. Then the error is computed with respect to the candidate with maximum visibility score, while bounds are defined as twice the 3 sigma empirical covariance. For a Zonotope shadow matching, the offline computation involves creating building Zonotopes, while online computation involves designing GNSS shadow Zonotope and iterative set differencing or intersection. We report error statistics with respect to centroid of the disjoint sets in the final estimate, while bounds are computed as the width of bounding boxes that individually enclose them. In the first set of results, we analyze the performance of the proposed ZSM by considering 8 urban buildings near Salesforce Tower, which is indicated over here and over here, and an initial set valued position estimate of size 120 meters by 120 meters, which is indicated here in magenta. As considered earlier, the satellites with blue circle markers are line of sight and the ones in yellow are non-line of sight. We iteratively refine the current set valued position estimate based on GNSS shadows that are indicated in cyan. For each satellite, we perform set intersection or set differencing by comparing CN0 against a predefined threshold, thereby indicating its line of sight or non-line of sight nature. Based on the final set valued position estimate, we can ascertain that the proposed Zonotope shadow matching estimates cross-street accuracy with small position bounds, which indicates high certainty. In this next slide, we compare the performance of the proposed Zonotope shadow matching with that of conventional shadow matching with a grid size of 10 meters. In this right figure, the color gradient of position candidates range from blue to red, with blue indicating low visibility score and red indicating high. We see a close resemblance between the receiver position estimated by the proposed algorithm and conventional shadow matching with maximum visibility scores. Therefore, our proposed ZSM algorithm successfully estimates position bounds that contain ground truth without requiring to perform point value discretization. Now let's look at some quantitative performance statistics of proposed ZSM, where we report the computational stats, the centroid of the two disjoint position sets, as well as the width of the bounding box that encloses these sets. For reference, the final set valued position estimate from our proposed algorithm is shown here in the top right corner. For conventional shadow matching, we considered two grid sizes of 30 meters and 10 meters, where grid size of 30 meters has one candidate with maximum visibility score that showcases a cross-street accuracy of 12 meters, while the grid size of 10 meters has two candidates with maximum visibility scores that exhibit cross-street accuracy of 2 meters. The bound for conventional shadow matching is computed using weighted empirical covariance, which are more than 100 meters in cross-street direction for both grid sizes. In contrast, we can observe that the proposed ZSM achieves high cross-street accuracy of 1.2 meters with a low bound value of only 5.8 meters. Note that parallelization can further improve the computational statistics of both proposed ZSM as well as conventional shadow matching. In this next set of experiments, we perform sensitivity analysis of our proposed ZSM by varying the number of buildings as 8, 10, and 20. In this table, we report 4 validation metrics that include centroid error, bounds, offline, and online computation load. In this left figure, we demonstrate the final set valued position estimate by using 20 buildings. Here, we see 5 disjoint position sets, of which one contains ground truth receiver position. We observe that as the number of buildings are decreased, the final set valued estimate also has lower number of disjoint sets. However, an interesting thing to note here is that other disjoint sets that do not contain ground truth can be easily ruled out by fusing proposed ZSM with other sources, say IMU or GNSS pseudoranges. So our proposed ZSM algorithm is easily scalable with respect to the size of the 3D building map considered. To summarize, in this work, we designed Zonotope shadow matching, in short known as ZSM, which is a novel set-valued approach for 3D map-aided GNSS that computes buildings and GNSS shadows using constrained zonotopes. Furthermore, we start with a core set-valued position estimate and refine it based on if receiver is inside or outside GNSS shadow. Through simulated experiments on 3D map of San Francisco, we validated that ZSM estimates high cross-street accuracy with high certainty. And we also demonstrate easy scalability as number of 3D buildings increases. We would like to thank National Science Foundation and Air Force Research Laboratory for funding this work. And we would also like to thank the members of NAV Lab for their insightful discussions. Thank you.